Hi, welcome back to Lussac Chemistry. This is on Gay-Lussac's gas hall lesson 8. Previously we learned that Gay-Lussac is a pressure temperature volume relationship where P1 over T1 equals P2 over T2. And like I said before, you should do it like this. P1 T2 equals P2 T1, which makes it linear and a lot more easy for us to process. Also, you should remember that temperature should be in Kelvin, not in Celsius. So if you get in Celsius, you've got to convert to Kelvin. And remember, if you have Celsius and you want to change it to Kelvin, Kelvin equals C plus 273.15. Okay, so now let's go ahead and let's talk about one more thing. What about volume? Volume is constant. We use K for constant, okay? So volume is constant, so we don't deal with volume in Gay-Lussac. All right, so what we're going to do next is we're going to work a couple problems with Gay-Lussac's law. All right, let's look at our first problem. A gas has a pressure of 0.370 atmospheres at 50 degrees Celsius. What is its pressure at standard temperature? So remember that it's P1 over T1 equals P2 over T2. So we're going to go P1, T1, P2, T2. And we're going to put our little equal signs there. Our first pressure was 0.370 atm. Our first temperature was 50 degrees centigrade. Our second pressure is what we're looking for. Standard temperature is 0 degrees Celsius. So that means we got to do some conversion here. We got to convert 50 and 0 to Kelvin. So let's do the first one. So we say K equals C plus 273.15. We're going to do P1 first. So that's going to give me 50 plus 273.15. And that's going to give me 323.15 K. So we're going to mark through this and go 323.15 K. Our second one is going to be K equals C plus 273.15. So P2 is going to equal 0 plus 273.15, which equals 273.15 K. Now we're ready to solve the problem. So we go P1 T2 equals P2 T1. We're finding P2, so we want to go P2 equals P1 T2 over T1. So P2 equals, let's see here, our first pressure is going to be 0.370 atm times our second temperature, which is 273.15 K, divided by our first temperature, which is going to be 323.15 K. So my K's cancel out, leaving only atmospheres left. After I do the math, multiply 3.70 times 273.5, then divide it by 323.15. Our pressure is going to be, let me go on the calculator here. Okay, it's going to give me 0.31 atm. All right, let's look at one more problem. Okay, so in this particular lesson, so let me clear the drawings and write a new problem. Okay, in this problem, a gas is cooled from 323 Kelvin to 273.15 Kelvin, and the volume remains constant. If the original pressure of 750 millimeters of mercury was the final pressure. So again, remember that it's P1 over T1 equals P2 over T2, which is the same as P1 T2 equals P2 T1. So now our P1 T1 P2 T2. So let's find out what our volume is, what our, not volumes, but let's find out what our players are. That's what I meant to say. Okay, the first temperature is 323 K. It's going to cool down to its second temperature, which is 273.15 K. And putting this into this little chart is the hardest thing because you have to learn how to read the problem. The original pressure is 750 millimeters of mercury. Now, do we have to change that to atmospheres? No. But at the temperature Celsius, we definitely have to change that to Kelvin. What is the final pressure? Okay, well, that's what we're going to look for. So P1 T2 equals P2 T1. So P2 equals P1 T2 over T1. So P2 equals our first pressure, 750.0 millimeters of mercury, times our second temperature, which is 273.15 K, divided by our first temperature, which was 323.0 K. Now our K's cancel out, and when we get busy on the calculator, this is going to give me a pressure of 634.25 millimeters of mercury. Now, could I turn that into atmospheres? Sure, I could. If I really wanted to do that real quick, let's see here. I'm going to go 634.25 millimeters of mercury times 1 ATM. There's 760 millimeters of mercury to every atmosphere. So that cancels out. Get my calculator again. I'm going to go this. Which will give me approximately 0.83 ATM. Well, that's it for this lesson. You guys be snarly. We'll see you back here at Moose in Chemistry.